Hello and welcome to this video on the exercises for the course of Machine Dynamics. Today we will have a look on animations for the Jeffcot rotor or Laval rotor. Let's look on the first example. This example, we see the system with the rotor which is mounted on the shaft. The shaft is fixed at the two bearing points. So we don't consider elasticity yet at those points. We can derive the equations of motion, as you can find in the lecture notes and in the exercises. In this standard form, we can see the external damping here, and we can see the omega k, the natural frequency, which is in this case C/M. In the figure here, we can see a blue point and a green point, where the blue point is the point where the rotor is mounted on the shaft, and the green point is the center of mass of the rotor. And those points are not necessarily at the same position in reality. That's why we can observe the effects that we will see in the animation. So in the animation, we start with very low angular frequencies, and we can see that the center of mass starts to rotate around the center point, the blue point. So we see that the amplitudes start to increase, so the blue point starts to move. And we also see a phase shift occurring. So a phase shift which was originally 0 and will end up at a value of pi. So now we pass through the resonant frequency with very high amplitudes. And if we increase the frequency, we see that the green point approaches the gray point, which is at the connecting line between the two bearings again. This is called the self-centering effect. Let's move to the next example. In this example, we also consider elasticity at the bearing points. So at this point and at this point. So we have a horizontal spring in the model here and a vertical spring, and the same on the other side. And we consider different stiffnesses for the horizontal spring and the vertical spring, but the same stiffness on the other side. So what happens? The equations of motion stay about the same, as we can see, but we have the value omega k1 and omega k2 changing compared to the example from before. So we have omega k1 and omega k2 to be two different natural frequencies that can be calculated with the formulas here. And in these formulas, we see the value for CH, which is the horizontal stiffness, so the stiffness of the horizontal spring, and we see the value CV, which is the stiffness of the vertical spring. So in the first animation, we will consider the case where both stiffnesses CH and CV are the same. So we have isotropic bearings. Again, we start with very low angular frequencies and increase the frequency. We see the center of mass rotating about the origin. And now we see also that the bearing points start to move. We approach the resonant frequency, which is at a lower angular frequency as before, because we reduce the stiffness of the system. And we observe the same for the phase shift. So the phase shift is also shifted to the left in this diagram. And again, we observe the self-centering effect. So the green point moves towards the center line that we can see here. So in our last example, we will consider different stiffnesses in horizontal and in vertical direction. That means we will end up with two different natural frequencies, so two different resonant frequencies, depending on the direction that we observe. So if we look, for example, at the horizontal amplitudes, we will have a different frequency where maximum amplitudes occur compared to the vertical direction. But again, the same effect, the self-centering, occurs here as well. So that was the last animation for this video today. Thank you for your attention.